Hi, I'm Talia Gillis from Columbia University, and I will be talking about joint work with Jann Spiess and Bryce McLaughlin from Stanford University, in which we discuss some results on fairness of algorithms with respect to how they're applied. When we analyze the fairness of algorithms used for decision-making in critical domains, we need to pay attention to how an algorithmic decision is applied. One way an algorithmic prediction is applied is by directly translating the prediction into a decision. Suppose we've trained a model to predict borrower creditworthiness, so that when we have a new applicant, we provide the model with their features, which then translates into a decision with respect to the borrower's credit limit. We call this automation. And a significant part of the algorithmic fairness literature and much of the legal and policy literatures focus explicitly or implicitly on analyzing a prediction when an algorithm implements a decision directly. But in many critical applications, we see a very different model in which a prediction is given to a human decision maker that has decision-making authority. For example, you could have some algorithmic recommendation, like a prediction of creditworthiness, but a human would decide the credit limit. We call this assistance. And this model of decision-making, in which an algorithm acts as a decision aid to a human decision maker, is prevalent in many critical decision-making domains, such as employment and bail decisions, and is often mandated by legal rules. So in our paper, we can compare some of the results of the algorithmic fairness literature to their counterparts in a decision system where a human decision maker takes the prediction as an input. So in our paper, we compared two very simple algorithms, essentially conditional averages, which vary based on whether they use a protected characteristic focusing on gender to inform some prediction. And we have two main metrics of interest. For our fairness metric, we look at the expected difference in how the decision system or decision maker is going to be implementing the decision across gender, holding all other features consistent. So think of X as a large covariate set. And for accuracy, we look at the expected mean square error of the prediction. And we compare these two metrics when we include and exclude the protected characteristic in two decision systems. With automation, when the decision itself is the conditional average, and with assistance, where the decision is determined by a human who has some prior beliefs seeking to maximize accuracy after seeing the conditional average. And our key results are that for automation, using gender to form a conditional average increases disparity. And this is simply because it allows a direct differentiation based on gender. And this is the classic trade-off between accuracy and fairness. But under assistance, the causal effect of including gender completely depends on who is getting the signal. And to demonstrate this, we focus on a context of a decision maker with an inaccurate statistical bias. In such a case, the use of gender in the conditional average can decrease disparities, creating an alignment between risk minimization and fairness. So to clarify, we're not arguing that including a protected characteristic can always reduce disparities. Rather, it can. And that's because when we consider the impact of an algorithm, we have to be sensitive to how it's going to be implemented. When we choose or are required to use algorithms as an input rather than as a decision maker, we must evaluate the combined impact of the human and algorithm rather than treat the algorithm as the be-all and end-all of a decision. Thank you.